Hello, everyone. Thank you for joining us. Hope everyone is safe and healthy wherever you're joining us from today. My name is Jeremy Foster. I'm with the United States Agency for International Development, and welcome to today's webinar, Clean Energy Technical Solutions for Power Sector Resilience, brought to you by USAID's partnership with the U.S. Department of Energy's National Renewable Energy Laboratory and its Resilient Energy Platform. Before we begin, I would like to briefly introduce the USAID NREL partnership, as well as the GoToWebinar platform before. USAID and NREL partner to deliver clean, reliable, and affordable power to the developing world. The USAID NREL partnership addresses critical aspects of deploying energy systems in developing countries through policy, planning, and deployment support, as well as global technical platforms. Through the USAID NREL partnership, we've built a portfolio of global technical platforms that provide free, state-of-the-art support on critical challenges to scaling up advanced energy systems. These platforms include the Renewable Energy Explorer, Greening the Grid, the International Jobs and Economic Development Impacts Model, and the Resilient Energy Platform. The Resilient Energy Platform provides expertly curated resources, training materials, tools, and technical assistance to enhance power sector resilience. The platform enables decision makers to assess power sector vulnerabilities, identify resilient solutions, and make informed decisions to enhance power sector resilience at all scales. More information on the platform can be found at the website shown here. Before we begin, I'd like to go over a few housekeeping issues and quickly introduce some of the webinar's features. For audio, you have two options, either your computer or your telephone. If you use your computer, please select the microphone and speaker option on the GoToWebinar audio pane. If you use your telephone, please select the telephone option on the GoToWebinar audio pane, and then use the telephone number and access code on the right side of the display. Listening by telephone will usually provide the best audio connection. If you have technical difficulties, please contact GoToWebinar's help desk by dialing the number on this slide. We welcome questions from all participants of this webinar, which we will address at the end of the presentations. If you have any questions, please type them in the GoToWebinar question pane anytime during the webinar. Within a few days, we will share a recording of the presentations via email and on the USAID NREL Partnership Learning channel on YouTube, which can be accessed at the link provided here. On this YouTube channel, you can also find other informative resources from the USAID NREL Partnership. Finally, I'd like to introduce today's presenters. Eliza Hotchkiss, Senior Resilience Analyst with the Resilient Systems Design and Engineering Group at NREL. Stuart Bannister, Renewable Energy Coordinator with the Barbados National Oil Company, and Roberto Acosta, President of the Accurate Solutions Corporation. After the presentation, the webinar will conclude with a question and answer session. And with that said, I will hand it over to James Ellsworth with NREL, who will be moderating our discussion today. Thank you.
All right, this is James Ellsworth from NREL. We'll start with Eliza Hotchkiss presenting on technical solutions for power sector resilience.
Great, thank you both. Good morning to everyone for joining us today. And as Jeremy mentioned, my name is Eliza Hotchkiss and I'm a Senior Resilience Analyst here at NREL. Today, I'll be presenting a few high-level concepts related to technical solutions for resilience within the power sector. And then I'll hand over the webinar to our guest presenters to speak about their real-world examples. Before we dive into solutions, though, I wanted to start with the definition for power sector resilience, which is the ability to anticipate, prepare for, and adapt to changing conditions, and withstand, respond to, and recover rapidly from disruptions. Resilience planning identifies the threats and hazards, vulnerabilities, and impacts to the power system and devises strategies to mitigate those. The technical solutions discussed later in this presentation address many threats, hazards, and vulnerabilities, and we'll talk about how they do that. The Power Sector Resilience presentation that was given through this platform in August of 2019 focused on the Power Sector Planning Guidebook for practitioners. The guidebook details a holistic process to engage stakeholders, identify vulnerabilities, and implement critical actions to enhance power sector resilience. The final step in this guidebook is to develop and prioritize resilience action plans, which include some of the solutions that we'll be talking about today. Today's presentation will focus just on those technical solutions, but if you're interested in seeing this webinar or other materials related to the Power Sector Planning Guidebook, please visit the links that Jeremy presented earlier today. To understand effective solutions, it's necessary to understand vulnerabilities and the impacts first. Power sector vulnerabilities are weaknesses within infrastructure, systems, or operations, and they're susceptible to natural, technological, and human-caused threats. The impacts from these threats include power or water outages resulting from physical infrastructure damage or sometimes aging infrastructure, fuel supply, food and water shortages, shifts in energy demand, and finally, ancillary financial, economic, and social implications of failures within the system. Keeping vulnerabilities and impacts in mind, we will focus on 5 specific resilience strategies shown in the outer ring for the resilient power sector. Starting with energy end use management, we will work clockwise around the strategies. The first of those is energy use management, and sometimes this is called demand side management, and it's often overlooked in power sector resilience strategies. However, this solution can support both short and long-term goals during normal operating conditions and during grid outages. Demand side management is the modification of consumer energy use through education, behavior change, energy efficiency measures, financing incentives such as utility tariff structuring, and all of those measures during short-term extreme events can help reduce peak loads as well as the need for increased generation over time. This technique can reduce the loads needed to be met by on-site generation or battery storage capacity, which could be operating during a grid outage. Good utility scale demand side management and approaches such as improved energy efficient building codes can support a more resilient power system. The concept of passive survivability may not be familiar to many people, so we'll talk about that in the next slide. Passive survivability is a term that was coined by architect Alex Wilson in 2005 after Hurricane Katrina. The term refers to a building's ability to maintain critical life support conditions in the event of extended loss of power, heating, fuel, or water. This idea incorporates ways for a building to continue sheltering inhabitants for an extended period of time during and after a disaster situation. While many of these strategies considered to achieve the goals of passive survivability are not new concepts, such as energy efficiency, as you'll see on this slide, the distinction comes from the motivation for moving towards resilient and safe buildings. This image shows the relationship between older architecture, conventional houses, Energy Star rated buildings, a U.S. Department of Energy program for efficiency called the Building America program, and then passive house standards. This shows the cost of ownership, but highlights the improved comfort, air quality, and efficiency. To become net zero, which would be the next step after being a passive house, an on-site energy generation source is needed, such as solar panels. And it's recommended to reduce energy consumption as much as possible through building efficiency standards before installing renewable energy technologies, which I'll discuss next as a solution for resilience. The next strategy we'll cover, as I mentioned, is power generation. And similar to the table shown in the energy end use management strategy slides, this table includes an effective resilience solution of on-site generation with energy storage. This solution realizes more cost savings, can support local renewable energy goals, and can also reduce the likelihood of service disruptions due to demand spikes during normal operating conditions. During a grid outage, on-site generation with energy storage can provide continued operations, potential for long-term operation, and a reduction in impact of the grid outage to users. But it can also help grid operators focus on other areas that will need faster power restoration. Two strategies to consider within power generation solutions is diversifying generation sources to help alleviate potential risks and reduce impact. This includes having more than one type of power generation source within a portfolio, and then distribution of generation sources can mean decentralizing or geographically distributing them. This can be an effective solution in mitigating physical hazards and threats. For example, if a tornado wipes out a power source, if the generation sources are spread out, the chances of all of them being wiped out are reduced. And I'll talk a little bit more about both of those in the following slides. Resilient power systems often incorporate a diverse portfolio of electricity generation technologies to increase reliability and allow for service disruptions to be mitigated and resolved quickly. As part of a portfolio diversification strategy, renewable energy technologies can provide a power source that is harder to disrupt relative to traditional or conventional technologies. Relying on any one source of energy can create an unnecessary vulnerability within a power system. Utilizing appropriate renewable energy technologies and storage solutions, and in some cases, pairing those with fossil fuels in a hybrid system, can enhance the resilience of a system. The solutions presented here are system-specific. Power system planners and operators should obviously undergo a vulnerability assessment and a feasibility assessment to develop a resilient strategy that is specific to their vulnerabilities and needs. Decentralizing energy sources is another technique used to enhance power system resilience. On-site renewable energy generation or other generators can reduce the disruption to a site related to a grid outage, mitigating the impacts of a long-term outage. Microgrids are typically implemented where on-site renewable energy is combined with energy storage to support resilience. Systems that are designed to operate in islanded mode can be isolated from a larger grid, allowing the system to generate and distribute energy on-site in the event of a power outage. The capability of microgrids to operate in islanded mode can be critical in supporting resilience by providing a backup resource during a grid outage, but also allowing certain loads to be covered as linemen restore the larger grid. An additional benefit of microgrids is that they can be designed to provide power specifically to critical loads, such as healthcare facilities or water treatment plants during a grid outage. While energy storage is a component of the power generation strategy, I'll talk a little bit more about that in this section because it is an important technology to highlight. And integrating energy storage into electricity grid systems can smooth variation in renewable energy sources, such as wind and solar generation, while adding redundancy to the grid in the event of power outages. When distributed systems with battery storage are connected to the larger grid, they can be designed through interconnection agreements with a utility provider to include islanding controls and energy storage to allow for grid disconnection that enables operation behind the meter without backfeeding power to the larger grid. And that's really important for safety reasons for any linemen who are working on the grid. This configuration allows for independent operation during grid outages. While the most common energy storage technologies are batteries, as you see on the slide, there are some other storage methods, which include flywheels, compressed air, energy storage, and pumped hydro. While energy storage is a key component of microgrids, it's important to consider whether storage solutions can enhance resilience on the larger grid as a whole. While distributed or microgrid renewable energy systems can be incorporated without energy storage, adding the flexibility of energy storage technologies could allow microgrids or critical loads to operate for longer periods of time without grid connection by having that energy storage. Asset protection is the fourth strategy I'll discuss today, associated with power sector resilience. And understanding where the most at-risk assets exist within the power system will help with activities such as relocating assets above flood levels and away from potential high-risk areas, such as along coastlines. So a lot of the common mitigation measures that you'll see is moving substations inland and upland, or burying underground aerial lines. If you have overhead lines that are at risk from high winds, it might make sense to bury those. And sometimes we've seen in certain cases that critical facilities have their lines buried first. And those could be lines that serve medical centers or emergency shelters. Cybersecurity is another method for protecting valuable assets by ensuring protocols and security architectures are robust, up-to-date, and obviously in place and practiced. We have more in-depth resources available for cybersecurity frameworks for distributed energy here at NREL, which we won't get into today, but I wanted to bring it up because we do have a number of resources in this area if anyone is looking for those materials. And then the fifth and final strategy I'll discuss is incorporating smart grids. A smart grid provides two-way communication and flexible control within an electricity network to support flexibility, efficiency, and resilience. In many ways, smart grids can bring together all of the technical solutions that were highlighted previously in this presentation under a more resilient electricity system. Through automation, technologies or devices within a smart grid collect data in real time that can be analyzed by utilities and system operators. Grid technologies or nodes can then be controlled and altered based on the data received and analysis of the situation. For example, because of real-time communication on changing needs and circumstances associated with an extreme storm or other disaster, responses and decisions regarding new power needs and power diversion can be made quickly. Smart meters could allow for responsiveness by sending data directly from electricity meters to energy providers and can enable islandable systems to support resilience during disasters or grid outages. Additionally, reducing peak loads can lessen system instability and stress during extreme events and can reduce the need for increased electricity supply over time. So with any smart grid control system, though, it's important to factor in cybersecurity measures to ensure secure communication between devices, but also ensure that this equipment is installed well so that it's able to survive a lot of those threats and hazards. With all of these solutions, they should be site-specific, meet the energy loads, and consider critical loads as a prioritization method. As we've seen in hurricane-stricken areas, it is essential to ensure that any power generation technology is installed well and securely so it can survive a number of threats and hazards. And finally, please remember that there is no one-size-fits-all approach to solutions for resilience. They will need to address your specific threats, hazards, and vulnerabilities to reduce the impact to the power sector as a result of a threat or hazard being realized. And with that, I'll now turn the presentation over to Stuart.
Thank you very much, Eliza, for that. Good morning, everyone. And I take this opportunity to thank NREL for allowing me to share our story in Barbados of the DREAM project. I was a technical officer on the project. So the project Disaster Risk and Energy Access Management, or DREAM project, as it's called, I'll be sharing that story of building resilient communities today. So a bit of overview and agenda of what I'll be discussing this morning. I'll be giving an introduction, an overview of the DREAM project, the project implementation partners and funding agency. I'll be taking a look at the photovoltaic installations that were installed under the DREAM project, showing some photographs of the installations at the community centers, pavilions, and polyclinics that we would have done. Looking at building capacity at the community level and what that meant for the project, and looking at building that capacity in solar photovoltaic installation and maintenance, and also sharing some photos of that training course. So a bit of introduction. Barbados has a population of approximately 285,000 persons. Barbados is a small island developing state and has a land area of 166 square miles. The electrical grid has a total capacity of 239 megawatts, predominantly using imported fossil fuels to generate electricity. We currently have 40 megawatts of renewable energy on the grid, 30 megawatts of distributed solar photovoltaic systems, and 10 megawatts of utility scale solar PV, which is owned by our local utility, the Barbados Light and Power Company. The annual electricity production is approximately 944 gigawatt hours, and it's important to note that Barbados is prone to tropical storms and hurricanes, and this plays an important role in building our resilience and disaster response, which was done through the project. So a bit of just context, showing the location of where Barbados is. So Barbados is located in the Caribbean. We're located on to the west of the island chain. Barbados is kind of unique in that most of the islands have some volcanic or geothermal potential. Barbados is unique in the sense that it's predominantly coral and rose from the sea, and we have a unique geology on the island. So just that, a little bit of context of where Barbados is in the world. Now, a little overview of the DREAM project. So the DREAM project was divided into three main components. Component one, looking at the renewable energy policy framework. This aimed at improving the licensing framework for the deployment of large-scale renewable energy projects. Component two looked at clean energy capacity development. This is where we focus our efforts on developing community-level training, and also looked at fostering or engaging the public to further advance the knowledge and exposure of renewable energy in Barbados through 2 energy expos we would have developed and put on as part of our Energy Month activities. Component 3 looked at solar photovoltaic installations, and this was focused at the community resource centers and sports pavilions around the island, 22 of them, and all polyclinics on the island. The project commenced in June of 2015 and was completed in November of 2019. The project budget was 1.7 million US dollars, and this was grant funded. So we're now to look at the implementation partners and the funding agency. So the implementation partners were the Ministry of Energy and Water Resources, and which is a government agency, and the United Nations Development Program in Barbados and the OECS. And the funding agency was the Global Environment Facility, or GEF, which offered the grant funds, and that was in the GEF 5 cycle of projects. So now look at the DREAM project's photovoltaic installations. So the first phase of the installations focus on the community centers and pavilions. with a total of 22 systems being installed with a total capacity of 70 kilowatts. These systems are hybrid systems with battery backup, with an approximate size of battery bank between 20 kilowatt hours to 40 kilowatt hours. At the community centers, we designated different loads or critical loads to the batteries, such as electrical sockets to power telecommunication devices, and lighting for offices and hall areas and other bathroom facilities within the centers, so that they would have emergency power in the event there's an outage. The second phase of the project, in terms of installations, looked at installing photovoltaic systems at all 9 polyclinics on the island. These systems were also hybrid systems interconnecting with the diesel generators at the polyclinics, with a total capacity of 172 kilowatts. The polyclinics all have 100% diesel generator backup. So the aim of the project was to allow those generators to have a longer runtime and to offer fuel savings. So the purpose was not only to reduce the electricity consumption at the polyclinics in terms of from the grid, but also to provide those generators to run longer in the event there's a grid outage. So now looking at some photographs of these installations at the community centers and pavilions. So to the top left of the screen, we're looking at the 7.5 kilowatt peak photovoltaic system at one of our resource centers in the south of the island. To the right of that, we're looking at a 5.0 kilowatt system. These are the 2 hybrid systems with the batteries at one of our sports pavilions in the center of the island. And an example of the battery bank is to the bottom left of the screen, and they use AGM batteries, and all the batteries were encased in a protective box, which was lockable, and to ensure their safety and protection as well. And then lastly, a photograph on the bottom right of this screen. You're looking at a hybrid inverter that was used along with the charge controller and data logger. So some photographs of the photovoltaic installations at the polyclinics. On the top left of the screen, you have a 15 kilowatt peak system at the St. Philip Polyclinic in the south of the island. And then one of the largest photovoltaic installation that we did under the project was at our St. John healthcare facility, and that is a 51 kilowatt peak installation. And then to the bottom left of this display is a 13 kilowatt system at one of our polyclinics in the center of the island called the Glebe. And to the bottom left of the display is an example of the 66 kilowatt inverter that's used at the St. John facility. Just a note, these systems under the polyclinics all use optimizers to enhance the performance of the systems, and the inverter used was Solar Edge. So now looking at building capacity at the community level. So the DREAM project was tasked with developing a training course. One of our stakeholders, the community development department, had really insisted that we focus and develop this course for the advancement and uptake of renewable energy in Barbados. So we reached out to the Technical Vocational Education and Training Institute, the TVET Council, to develop a solar photovoltaic installation level 1 MVQ. So it's accredited program on island, and the target group for the project was the youth and underemployed, and the aim of the course was to increase the knowledge of solar photovoltaic installation and have persons who are properly trained in basic solar photovoltaic maintenance. Now, we ran a pilot within the project, and 13 persons completed that training, and we had engagement with the private sector as well. So there was a number of private sector companies, photovoltaic installation companies, who came in and partnered with us in terms of donating photovoltaic equipment, tools, and safety equipment for the program. And a number of these companies also offered internship opportunities. So when um, the persons completed the training, they would be given an opportunity to apply their skills, that they were newly acquired skills, in a real world scenario. So that was important for us to have not only the private sector involved and in the donation of equipment, but also allowing and giving the opportunity to these persons to have some real life training and experience. So now, lastly, we're gonna just take a look at the photographs of the training. So to the top left of the screen, we just have a couple of the students holding a photovoltaic module along with some racking. And then to the left of that picture, we have some of the students in their personal protective equipment, which is important. Safety is always paramount as we install these systems, and they're measuring some of the racking to be installed. And then lastly, at the bottom of the display, we have the graduation ceremony where a number of the students would have received their certificates and would have been lauded for their efforts and being pioneers in this new level 1 photovoltaic training. Also must be noted that approximately, I think, 9 of the persons who would have completed the course level 1 went on to do the level 2 course, which is offered at our local technical institute, which offers level 2 and level 3 training. So those persons saw that they enjoy the program so much that they were encouraged to go on further and develop their skills even more. So that was encouraging, and we hope that this is now a start, that we can have more Barbadians involved within the solar photovoltaic industry who are trained and understand the best practices, not only in installation but in safety. Thank you very much. I'll now pass on to my other colleague Roberto to discuss the Puerto Rico case study. Thank you.
Okay, thank you, Stuart, and thank you to all of us all joining us in this presentation. This first slide was how we started our CHP project initiatives, stressing out to control the energy budget while reducing costs and environmental footprint. This statement actually undervalues the business continuity. You will see the social impact of keeping the hospital running. Our first project and case study being presented was indeed a much higher benefit. So on the next minute, I will review some facts about Puerto Rico, our electric grid status, our history of resiliency experiences, and the energy cost projections that motivated this CHP study. The system architecture will also be shown, along with the benefit achieved, finalizing with the challenges or next steps we face. Puerto Rico is the third largest island in the Caribbean, a U.S. territory with about 100 miles by 35 miles, with a population of 3.3 million. We get many hours of sunlight and a nice warm average temperature of 80.6 degrees Fahrenheit. Even though our government is at bankruptcy, PREPA and the utility grid bonds are also on dispute, we have a large industrialized economy. We are, in fact, 4 times smaller in area and 3.1 times smaller in population than the Dominican Republic, but we consume 15.6 times more energy. PREPA, a government monopoly, has been the only electric provider for many years, and I must say in the past helped Puerto Rico industrialization and economic development. With 2,460 miles transmission lines, about 31,000 miles of distribution lines, 238 substation at 38 kV, 51 substation at 100 kV, and 5.8 gigawatt of generating capacity, PREPA was a highly ranked company. Still today, consumed from PREPA, Puerto Rico consumed for PREPA about 70,000 gigawatt of electricity per year. 32% of that is residential customers, 47 on commercial, and 13 on industrial. PREPA have also 101 megawatt in wind, 212 megawatt in PV, 2.4 megawatt from landfill gas, and I estimate about 30 megawatt of additional PV that may be informally installed. So, with several aged power plants, some of them range from the 60s and 70s. The average power plant efficiency in Puerto Rico is 34.97%. So billions of dollars are wasted in losses. The largest plant is in the south, Costa Sur, while the load is connected on the north, the metropolitan area. Finally, there are large power plants spread through the island, requiring thousands of miles of power line, decreasing resiliency and increasing operational cost. So this definitely is not good, considering our history of hurricanes and also atmospheric events. In January 7 of this year, a few months ago, a 6.4 magnitude earthquake led to a complete blackout of when Costa Sur, the largest plant, went offline due to the earthquake's proximity. And trust me, bringing up the grid is not an easy task. Or without Costa Sur, the largest power plant. In September 20, 2017, Hurricane Maria destroyed the whole transmission and distribution network, making the longest and largest blackout on U.S. history, and the second largest blackout in the world on record. For more than a year, several regions were without power, and the host island experienced many blackouts through 2018. Not all blackouts were weather-related. In September 20, 2016, a year before Maria, a major blackout occurred when a main substation caught fire. Well, basically, it almost exploded. In a good year in Puerto Rico, a typical generator will run at least 120 hours per year, and there have been several occasions that customers have exceeded the 500 hours per year limit established. This leads to the inevitable unreliable power and low power quality. This chart shows the power disturbances measured from the grid intertie protection relay in the CHP plant at San Germán for about a year. Some months, up to 24 events were registered, almost one per day. The events were triggered on a wide voltage and frequency fluctuation, a deviation for about plus minus 1 hertz, and about 10% on voltage. This type of power quality deviation caused many damage to equipment to many PREPA customers. As an example, the 16 chiller at the hospital, before we were just starting the project, was seriously damaged by a PREPA power quality incident with over $180,000 in estimated repairs. Those repairs were minimized as the project already was starting, and the new chiller that was ordered for the project was temporarily connected. But what really makes the managers crazy is the uncertainty. There's no statistic or mathematical course to keep with PREPA fluctuating costs. There is actually way to forecast it. One thing is certain: cost in Puerto Rico will be higher than 23 to 25 cents kilowatt hour when considering debt service for the next 40 to 50 years. A high price tag for an industrial economy competing globally. This chart is one of the many projections used for the electrical cost for the years to come. It won't be flat as shown, but at least this one shows a more realistic cost. Hospital de la Concepcion in San Germán, when we installed the first CHP, were the leaders in CHP adoptions. They are a medium-sized hospital based on the island scale basis, considered an acute care hospital that a principal facility and the principal facility for the southwest region of Puerto Rico. The facility has about 220,000 square feet, 167 beds, and they serve, except advanced cardiology and cancer treatment, they provide all medical services. The electrical energy consumption was 10.83 megawatt per year, with a maximum demand of 2.1 MVA or 1.75 megawatt. The average demand was 1.8 MVA or 1.5 megawatt. The cooling need from the chillers is 561 tons on average, with a maximum demand of 745 tons. Water reheats are used for the tight humidity controls required in the facilities. The reheat loop uses about 326 kilowatt of thermal as maximum and 186 kilowatt as an average. The theory behind CHP is to effectively recover the waste heat from the electric generation plant. This is the system. In this system, the electric efficiency is 40%, 5% higher than PREPA efficiency, and that efficiency does not include the transmission and distribution losses that actually are twice the U.S. average. Now, 83% of that 60% that is wasted or is normally wasted is recovered. And there are many ways to recover it. We are recovering to chilled water and hot water. Please note about 50% of that wasted heat is a non-recoverable surface heat, since Puerto Rico do not have any space heating possibilities. This is what makes CHP a highly efficient, attractive system, ranging from 80 to 85% as a typical efficiency, while making a significant environmental benefit due to less fuel consumption while running cleaner fuels. Compared to a 60% best available combined cycle gas turbine system, a good CHP operates 42% higher than the thermodynamic returns on a combined gas cycle turbine. There are many ways to recover the heat, as I mentioned. Chilled water was the major hospital need, but steam, hot water, or even additional electricity could be generated. This is a slide from the DOE webinar where it shows several recovery options. Okay. The system block diagram that was used with some live data in the hospital is being presented. As an example, the fuel will go from this green line to the generators. There are two generators, one backup of the other, and electricity will be produced. That will be the first power available from the fuel. So, as it is mandatory, right? This process will generate heat, and there's three types of heat: on the exhaust gas, on the jacket, and on the second stage intercooler of the turbo. So the exhaust gas is diverted to an absorption chiller, okay, and the high temperature jacket water is also diverted to the absorption chiller. With those two, that heat is converted to a maximum capacity of 350 tons when the plant is operating at maximum capacity. And the low-grade heat from the second stage intercooler is through a heat exchanger exchange on the reheat loop, as I indicated. The electric chillers are in series, and this is advantage because the thermodynamic process that is occurring on the absorption chiller is low, and the electric chiller will make a fast response needed by the hospital. Notice that at this particular time, and the absorption chiller was not operating at best thermal capture, the efficiency of the system was 83%. And as a final notice, not on the electricity, this system supports a flicker-free transfer from the grid to island mode or vice versa. We finalized commissioning of the second generator about 6 hours before Hurricane Irma arrived to Puerto Rico, September 7, 2017. Even though the construction of the heat recovery building was not fully started, just the foundation. The hospital just disconnected from the grid hour before the power was lost due to Hurricane Irma. Maria got us disconnected, and from the longest power outage in U.S. history, we were fortunate. As the only hospital that operated full service without interruption in Puerto Rico, Hospital de la Concepcion became the host for the disaster relief team assistance from Hurricane Health Services and carry out all medical laboratory studies, surgeries for half of the island. The death toll during the hurricane was about 5 lives, but 3,000 people died due to the lack of care just after it. As an example, the owner of the company contracted to do the HVAC control on the heat recovery building died because he could not dialysis on time. He lives on the metro area. Hospital de la Concepcion saved 284 persons just by providing dialysis procedures. It was a great collaborative effort where the Armed Forces helped in providing additional supplies and doctors performed emergency services. From laboratory services to neurosurgeries, the social benefit of having a hospital in full operation was a much higher and greater benefit that we could remotely imagine. This is an aerial photo of the back of the hospital that serves the facilities of the cogeneration unit. Those white containers are the engines, and these are the dome radiators that if the heat is not consumed on the heat recovery building have to be dumped so they could continue its operation. This is the exhaust gas line transporting all the exhaust gas to the interior of the heat recovery building, and also the heat recovery lines are around there. And from the heat recovery building, these are the chilled water and hot water going to the hospital. The electrical is underground, and the main substation is in this area, in this corner. Okay. So on the achievements that we observe, on the technical achievement we observe on the hospital, we first applied the energy efficiency. So 18.9% of the demand was reduced just to efficiency improvement measures. Due to high electric chillers that normally operate at partial loads, pump efficiency in excess of 80%, and LED lighting that goes above 150 lumens. When the heat recovery is considered, the demand was reduced by 39.35% or to 894 kilowatt on average. Environmentally, we displaced 774 cars or 554 cars. The sulfur oxide emissions were reduced by 95% and 40% on greenhouse emissions. And those projections are for EPA compliant utilities, and PREPA is not an EPA compliant utility. As indicated on previous slides, the power production of central plants is a huge. The many millions of gallons of water are used just to cool the facilities where the heat is dissipated. This project saves about 1 million gallons of fresh water and 295 millions of salt water that will not be dissipated on the central power plants. The business continuity experience through Maria was uninterrupted, but through the 3 years of operation, we have had only 2 interruptions. And there were not big things. One is a seal of one of the pumps actually leave that the jacket water was discharged, and the pump operation was interrupted, and the engine was interrupted. And the other was a belt on the dome radiator. We have, shared our experience with FEMA, the Puerto Rico Energy Board, the engineers, and the other hospitals and institutions, so that this benefit is also shared to others. This is a photo of the interior of the heat recovery building. This is right in the back, the heat transfer package with the low-grade heat is transferred to the reheat loop. If for some reason it fails, then the condensing boilers, this condensing boiler will step in and produce the necessary heat. These right here are the electric chillers that are in series with the absorption chiller. And here You see, this is the assertion chiller. This is the output of the exhaust gas, where it is reduced from 950 degrees to 285 degrees. And this the electric chiller sitting behind it, and the other chiller is to the right. So we have shared the lessons and hoping for a resilient, distributed, collaborative, and open grid, where the experience lived during Maria are part of any facility, not just a hospital. Then creating what I call a new urban model for our society. For me, it is a smart grid, or better, a smart community. With that said, thank you very much for your patience, and now I leave you with James.
Thank you, Roberto, and thanks to Stuart and Eliza for the really informative presentations that all showed the huge positive impacts that clean energy technical resilience solutions can have for power sector resilience. This is James Ellsworth from the National Renewable Energy Lab and the Resilient Energy Platform, and I'll be moderating the question and answer section of the webinar. So thank you to all of our attendees for tuning in from all over the world for this webinar, and thanks for the questions you have all been asking. I will remind you that if you do want to ask a question, please type it into the question pane on the GoToWebinar control panel that is probably over to the right-hand side of your screen. And then we'll go through those questions and try to get to as many of them as we can in this question and answer session. So the first question is for Eliza. What is the difference between a hazard and a threat? And what are some examples of power sector threats and hazards?
Thanks, James. That's a really good question. The way that we define hazards is usually a source of danger. And while it's kind of nuanced, a threat can be a person, organization, or a thing that acts with intention. So whether or not it's realized, it is a threat, and it would exploit a vulnerability. And I'll talk about vulnerabilities in a second. But within the power sector, some hazards could include earthquakes, hurricanes, as was mentioned previously, tornadoes, and a hazard could be something like sea level rise or cyber attacks. So, for a threat, it could be sea level rise or cyber attack. So the way that we like to differentiate between hazards and threats and vulnerabilities is that a hazard or threat can't necessarily be controlled. All we can do is mitigate against the potential impacts associated with those. Whereas a vulnerability is a weakness within the system, which could be physical, technical, organizational, or operational, and those are things that we can control. So it's slightly nuanced. There are a lot of materials available. FEMA and the Department of Energy within the United States have a lot of useful and really informative resources around those topics if people are interested in learning a lot more about that.
All right, thank you, Eliza. We'll send our second question over to Stuart. A question about clarification on what are the resource centers, and then what resilience services do they offer, say in the instance of a grid outage?
Okay, thank you for that question. So the community and resource centers are, in the event of a disaster, they're used as relief centers. So they offer communication points throughout the island. So that's why it was critical to have the telecommunications devices installed or connected to the batteries, so that in the event there's an outage, that those telecommunication services will still be in operation. So that was important. And then they also serve as metrics for our places to distribute food and medical supplies as well. So it's mainly a distribution point and as well as a communication point in the event there's a disaster. So it was critical that we would have installed those battery-based systems to allow for that increased disaster response on island. That's it for me.
Okay, thank you, Stuart. Question 3 will be for Roberto. Have any other hospitals installed similar systems since the hurricanes because of the success of this hospital during the grid outage?
Okay, yes. There have been one additional hospital that have completed the installation of the CHP, and there are 3 ongoing projects on 3 additional hospitals that are implementing CHP, while several others are working on their final approvals. And not only hospital, but there are other facilities like data centers, hotels, and pharmaceuticals that are installing CHP or in the final steps to address CHP for resiliency.
All right, thank you, Roberto. We'll go back to Eliza for question 4. Let's see, cybersecurity should include not just the electrical assets, but also other components. These include customer or third-party equipment and programs, such as water or security systems or building management and so on. That could be a portal to the grid. Can you speak to this and how all of these can be included in projects?
Yeah, that's a great question, James. I know that with power systems and especially with smart grids, there are a lot of different avenues for entering the grid through cyber attacks. So one of the things that we highly recommend is making sure that you have a robust cyber framework in place. And that could include things like establishing a culture of security, making sure that your employees are trained to detect any sort of cyber threats and know what to do in those situations, but then also knowing that they are part of the solution and securing the system. But then also making sure that there is an assessment and that risk is constantly monitored, because unlike some of the resilient solutions that we've talked about, cybersecurity is something that is an ongoing process. It's very dynamic. Times are changing constantly. New threats are constantly arising. So it's important to keep an eye on those on a regular basis. Then developing and implementing protective measures that reduce those risks that have been identified, managing any incidents that arise, and then sustaining those security measures. Those are just the basic framework components, and applying those to each of the sectors that were mentioned in the question is going to be really important.
Great, thank you. Go back to Stuart with the next question. How did this DREAM project get initiated and funded, and what were its goals?
Thank you for that question, James. So the DREAM project came about from a need to increase Barbados' disaster resilience, and through collaboration with UNDP, the Ministry of Energy and Water Resources, and JEF, which was the funding agency, a project proposal was developed, and we approached the JEF, and the project was approved, our proposal was approved, and the project was developed, the project document was developed, and the project came into being with a need to improve the climate resilience and disaster risk management on island, and also with an aim to promoting solar photovoltaic installations in public buildings for the enablement of clean energy access. And that was done through the installation of photovoltaic systems at the community centers and polyclinics, which we would have done under component 3. So I guess the main objective or takeaway from the project is really to improve the disaster resilience of Barbados through those photovoltaic installations, as well as the disaster risk response in the event there is a natural disaster, that we can respond to those challenges with the grid potentially being offline, and to have resilient communities which can communicate and distribute key supplies in the event there's a disaster.
Great, thank you. Next question will be for Eliza. Could you please talk about the resilience risk of solar and batteries as a full solution?
The resilience risk of solar and batteries. If I'm understanding the question correctly, I think that some of the risks associated with solar and batteries are if the equipment isn't installed correctly or securely, that could be a potential problem. If the equipment isn't installed so that it can island from the grid, so that it can isolate and operate behind the meter during a grid outage, there could be a potential that those technologies could what we call backfeed onto the grid. So it's really important that those do have islanding controls, and that the utility is aware that those systems exist, so that they're not sending linemen out to restore power and having those systems backfeed onto the grid. I think some other potential risks associated with those is people just not knowing how those systems operate, and trying during a grid outage or some larger disruptive event, trying to get those systems back up and running without necessarily having the right technical knowledge. So it's really important to make sure that those are installed correctly, that there's communication with the utility and the site that has that type of equipment installed, and that those islanding controls are in place just to mitigate those risks.
Great, thank you. We have time for a few more questions, and if we don't get to answer any of your questions during the webinar, we will try to follow up with you and answer those questions in the follow-up email that we will send, that will include a recording of the webinar today. We will also post that recording and the slides on the Resilient Energy platform for anybody to reference after today. So the next question will be for Stuart. Do you have any experience synchronizing the solar and generators, for example, when high solar output results in low generator load?
I don't have experience per se with that exact example, but I could provide context of what we would have done in the Dream project in terms of when we interconnected our generators, our photovoltaic systems at the polyclinics with the generators there. So before we even started the installation process, we did a thorough assessment of each polyclinic, identifying key parameters. So for instance, the identification of where the PV modules will go in terms of roof space, where the inverters will be housed, looking at the cable routes and measuring the cable runs, and also gathering key information in respect of each generator or the genset. So looking at the manufacturer, the kVA output of the generator, ensuring that all the generators were serviced and in good working condition. So we work along with the technical management unit at the Ministry of Health and Wellness, and who are familiar with these generators. And then we also work with the installer or the company contractor who was tasked with installing the systems to ensure that the systems were compliant. The photovoltaic systems were compliant with the generators. So we ensured and we checked all the ATS controls, and so thorough checks were done to ensure safety of the equipment, both on the photovoltaic side and existing equipment, and to ensure that the systems meet code compliance on a national level. All the systems were inspected by our local government engineering, electrical engineering department before being connected to the grid, and also there are also requirements that before you interconnect the systems, that our local utility, Barbados Light and Power, also does inspections, and there's also settings on the inverters for frequency ride through and other different parameters which the utility would require. So there were a number of checks and balances that were done to ensure the safety and compliance of the system, working together with the generators.
All right, thank you. And we'll go to one more question here for Roberto. Any questions with fuel or any issues with fuel supply logistics for the hospital? And also, are there fuel reserves kept on site, and how much?
Yeah, for this first experience that we got, first project also in Puerto Rico for CHP, we had 7 days of local backup. So during Hurricane Maria, there were several bridges that were closed due to flooding, and actually we won pretty close, about like we were in the like 30 hours range that we needed to get fuel. If not, we have to switch to diesel. So as part of this extra contingency, we managed with the owner just to see the solution. So Hospital de la Concepcion now, every time there is a storm or anything running, they have additional moving containers that will add up to 15 days of additional storage. Other customers have installed 20 days of local storage, but the actual fuel distribution in Puerto Rico is pretty diverse. So depending on the fuel type, there's some fuels that could even last about almost 3 months without having to refuel from the external. To Puerto Rico, we don't have any fuels in Puerto Rico. Everything has to be imported. So we did experience sometimes. So 7 days may not be enough for an event like Maria. So, but we have created additional contingency either by providing temporary solutions until the hurricane season is ended, or by having in-house permanent fuel storage, maybe 15, 20 days at least.
Okay, thanks. So we do have time for a couple more questions. So let's see, one for Eliza, saying resilience is concerned with resource adequacy. While this is important, some of last year's extreme weather events showed that power system needs more than resilience, but flexibility to maintain system inertia within the limits. Resilience is kind of going against that as it calls for more decentralized resources, which would weaken system inertia. What do you think of that?
That is a really complex question. Let's see if I can untangle that one. So the way that we think about resilience in terms of spatial diversification or decentralized systems is that you have those either renewable energy or generation sources spread out in areas where you would need those resources. And that then takes that pressure off of the grid system. And we see those as being flexible if you have the right control strategies in place and communication networks in place. Those could add a lot of flexibility. So I don't know if that answers the question, but that's how we've been framing resilience in the power sector with those decentralized and distributed generation sources.
Okay, and we'll ask I'll ask one more question to wrap it up. What are some existing, and Eliza, you can take this, or any of the other panelists too can hop in. What are some existing governance mechanisms utilized across various countries to mainstream resilience in power sector planning?
Yeah, I can answer that one, James. That's a great question. There are a lot of examples available on what is being done in different countries. I think there are incentive programs and policies that are helping to guide those resilient strategies within the power sector. And a great place to find some of that information is something that Jeremy had mentioned originally at the outset of the presentation. But the U.S. Agency for International Development has partnered with NREL to create the Resilient Energy Platform. And all of the information that I presented about resilience technical solutions for the power sector are included in a fact sheet that we created on that. But then there are also a lot of materials, including a guidebook, some training and resources, quick reads, and there's also an Ask an Expert. I don't know why I can't say that this morning. Ask an Expert feature on that website so that you can ask a lot of these questions even after the webinar, and a lot of different experts will be able to respond to your specific questions. But that's a great resource. So if you search for Resilient Energy Platform, or if you have the link at the beginning of the webinar or the end of the webinar, that should be able to help you find some more of those materials.
Great, and that sounds like a good place to wrap it up for now. So thank you again to everybody in our audience for tuning in and for all your great questions. There were a lot of great questions we did not get a chance to answer, unfortunately, but we will try to reach out to those who ask questions and answer them via email after the webinar. And so with that, I'll pass it back to Jeremy Foster from USAID for some final words.
Hi, thank you, everyone. Thanks, James, and many thanks to our presenters, Eliza, Stuart, and Roberto. Really appreciate everyone's participation, as well as everyone who called in. Thank you very much for joining us. Before we go, I would like to invite you to keep in touch by following NREL on LinkedIn or Twitter. And also, please join the USAID NREL partnership mailing list with the link on this slide. These slides will be sent out, so you don't. You'll have access to all the links that we're providing. So once again, thank you to our presenters and attendees. We really appreciate your time and hope you can take some valuable insights back to your organization. So thanks again, and everyone have a wonderful day.